Hello, this is Dr. Nak. Today we are going to learn about rational functions. For prep work, please review how to write the solution set in an interval notation. I just wanted to let you know ahead of time that this section is going to be one of those long sections again. So do not watch this video in one sitting or your mind's gonna go bonkers. Let's briefly go over what we're going to be learning in this section. So first one is we are going to learn how to apply the notation describing infinite behavior of a function and finding the vertical asymptotes and horizontal asymptotes and the slant asymptotes. And at the end, we're going to use all these informations to graph the rational functions. Let's go over the definition of a rational function. It says, let p of x and q of x be polynomials where q of x does not equal to 0. A function f defined by f of x equals p of x over q of x is called a rational function. And the domain of the rational function is set of all real numbers excluding the real zeros of the denominator. So rational function is nothing but a polynomial over another polynomial. And poly means polynomial. And for example, right, let's take a look at this. So if I write like f of x equals 3x to the 5 plus 1. Now that's a polynomial of degree 5, right? This is a polynomial of degree 5. And I'm just going to make something up here. And then like maybe x minus 2. So again, this is also a polynomial of degree 1. So therefore, since we have a polynomial over polynomial, this function is called a rational function. In today's lecture, first thing, let's review how to find the domain of a given function and write our answers in an interval notations. After that, do not freak out. We will be learning about the end behavior of irrational functions and how to express the behavior. So all this crazy looking stuff right here, I will copy and paste when we talk about this topic. And after that, we will be learning about how to find the vertical asymptotes of a rational function and how to find the horizontal or the slant asymptotes. So here's the definition of the horizontal asymptote and then how to find it. And then we're going to talk about the slant asymptote, or sometimes we call this an oblique asymptote, but we'll get there. And then how to find where a graph crosses the horizontal asymptote. And what I did here under number 8 is basically I just summarized how to find all the asymptotes of a rational function. So you can kind of go through that. And then there's more. At the end, finally, we're going to graph a rational function by all these steps. So again, I will go over this as we talk about each topic. All right, are we ready to do this? Let's do it. Example 1, find the domain and write the domain in interval notations. So let's take a look at a few examples here. I know that we've done this before. So here we're given r of x equals 3x squared minus 4 all over x minus 5. So do you remember when we talked about the restriction of a given function? So it's basically the same thing. So what is the restriction? Well, if you have a fraction, you cannot have a 0 on the bottom, right? So that is going to be the restriction. So here we can write this as x minus 5 cannot be 0, so which means that x cannot be 5. So graphically, this is telling you that our given function is defined everywhere except at x equals to 5. Now let's write our answer in interval notation. So as I usually do, I just draw this cheesy number line. Here's negative infinity and infinity. So problem point is 5, right? So x cannot be 5. So I should have an open parentheses here. And then I shade everywhere else. Wherever that's shaded, that means that your function is defined there. So therefore, the domain of R is going to be from negative infinity to 5. Make sure this is an open parentheses. And then union open 5 to positive infinity. Let's take a look at this function here. F of x equals 1 over x squared minus 4. So again, we need to find the restrictions. So again, since this is a fraction, we cannot have a 0 on the bottom. So the restriction is that x squared minus 4 cannot be 0. By the way, there are a couple ways that you can do this problem. If you're comfortable factoring, then you can directly factor this into, let me just write them out. I don't know which way you like better. So this is same thing as x plus 2 and then x minus 2, by the way. So right there, boom, you already see the answer. But anyways, let me just do it this way here. So maybe you like it this way. So I don't know. So then let me just add 4 to both sides. Then here, what we're going to get is x squared equals to 4. Taking the square root on both sides, we're going to have x equals, be careful, we got to remember, plus or minus the square root of 4. So, which means that, oh, sorry, I should have a not equal to plus or minus 2. All right, so let's write our answer in interval notation. So again, I just like to draw the number line. So x cannot be plus or minus 2, right? So let's see, this is, pretend this is negative 2, and then this is 2, and then you better have an open circle around it and shade everywhere else. And just translate your answer directly below. So what is the domain of f? It's going to go from negative infinity to negative 2 open, and then union. Don't forget the middle part. You still got negative 2 comma 2, right? And then union, and then 2 to positive infinity. Next, let's do this one. We have g of x equals x cubed divided by x squared plus 1. So again, we have a fraction here, so we need to find the restrictions, which means that the bottom cannot go to 0. But think about it. Is the bottom ever going to go to 0? I don't think so, but if you didn't see that, do exactly the same as what we were doing so far. So here, restriction is that the x squared plus 1 cannot be 0, which implies that the x squared cannot be negative 1. Isn't this always true? If I square a real number, is that ever going to equal to a negative value? No. You'll get the imaginary answer here. So when this happens, this is telling you that you can plug it in any value of x. Of course, we're talking about the real numbers, and the bottom will never go to 0. So here, our answer is going to be, domain of g is going to be all real numbers. Now let's take a look at this one. We are given h of x equals x squared minus 1 over x minus 1. So again, the restriction is that the bottom cannot be 0. So x minus 1 cannot be 0, which means that the x cannot be 1. Let's keep that in mind. Now, do you notice that the numerator can be factored, right? So if I factor this, we can use the difference of two squares to get x plus 1, and then x minus 1, and then whole thing over x minus 1. Now, what is going on here? Do you see that we can cancel out the common factor, which is x minus 1? So if I did that, then let's look at our answer. This is just going to be x plus 1. Now, isn't that the polynomial of degree 1? And do you remember what the domain for the all polynomials are? It's always going to be all real numbers. So to find the domain, which one is it? Do we cancel out the common factor first or not? The answer is do not cancel out the common factors to find the domain. However, when you're able to cancel out the common factor here, right, like x minus 1 over x minus 1, solving the 0 of x minus 1, which is positive 1, we're going to have this thing called the removable discontinuity, which means that your graph is going to be y equals x plus 1. That's a linear function, isn't it? However, when x equals to 1, there is going to be a little hole on the graph. All right, so here is the graph of our h of x. Notice that this is the equation y equals x plus 1, isn't it? Because look, what's the when x is 0, right? Y is 1, x is 0, y is 1, correct? Now, let's take a look at when x equals to 1, and the decimal says that when x equals to 1, at that point, your y value is undefined. Therefore, this little circle is called a removable discontinuity, because if we remove it, it will be continuous. So the answer to the main question, find the domain of h of x, it's going to be settable real numbers except when x equals to 1. So let's try to answer this in an interval notation. So the domain of h is going to be negative infinity to 1. That's an open parentheses, and then union 1 to positive infinity. Our next topic is the end behavior of irrational functions. It says to determine the behavior of the function as x approaches infinity or negative infinity, and as x approaches value for which the function is undefined. We will use the following notations. Let's first look at the first notation here, x and then arrow c plus, c to the plus. So this is a notation for x approaches to c from the right hand side, but it will not equal to that constant c. Now, those of you who are planning on moving on to calculus, here is the formal notation to express this whole situation here. We say that the limit as x approaches to c from the right of our function f of x. Now, let's look at the next notation here, x arrow c to the negative sign. So this reads as x approaches to c from the left-hand side, but it will not equal to c. And again, in calculus notation, we say limit as x goes to c from the left of the function f of x. And this one's okay, right? X goes to infinity, so its meaning is that x approaches to infinity, which is same thing as x increases without a bound. So then notation for that in calculus notation will be limit as x approaches the infinity of f of x. And the last one is x arrow negative infinity. So this reads as x approaches to negative infinity, so x decreases without a bound, and the notation for that is the limit as x goes to negative infinity of f of x. Let's do some examples. Example 2, given the graph, find the following. So right here, we're given the graph of y equals 1 over x minus 5, and what is the restriction there? Isn't it x cannot be 5? So we'll learn this later on, but we will have a vertical asymptote at x equals to 5. Given the vertical asymptote, your graph is never ever going to touch it. Okay, so please keep that in mind, and let's do it. Part A, as x goes to infinity, where is our f of x going? So as x goes to infinity, right? Basically, this is asking you where is the tail end of the graph approaching to? And your answer should be the y value. So as x approaches infinity, this tail end is going to get closer and closer and closer to the x-axis, which is the same thing as y equals to 0. So therefore, as x goes to infinity, our function f of x is going to go towards y equals to 0, so just put 0. And in calculus notation, we will describe this as the limit as x goes to infinity of f of x. This is going to be 0. Part B, as x goes to negative infinity, where is our function f of x going? So here, as x is traveling towards negative infinity, right? Where is this graph going? Isn't it, again, approaching the x-axis, isn't it? That's where the y value is 0. So as x travels towards negative infinity, this tail end of the graph is going to go towards y equals to 0. So let me just write that answer. So f of x is going to go to 0. And again, in calculus notation, we write this as limit as x goes to negative infinity of f of x equals to 0. Part C, as x approaches to 5, remember this plus sign, from the right-hand side, where is the tail end of the graph going? So here is x equals to 5. Now, as x travels towards 5 from the right-hand side, so what we're doing is we're going to travel from here all the way towards 5. And the question is, where is this tail end going? So isn't this, what's the y value here? Isn't it keep going? It's going to keep going and going and going and going. So y value is eventually going to go to infinity. So as x goes to 5 from the right-hand side, then our y value, which is our f of x, is going to go to infinity. So here, let me just write that as f of x is going to go to infinity. Let me just color code this. So as x approaches to 5 from the right, what we're looking at or analyzing is this tail end of the graph. Now, using the calculus notation, we write this as the limit as x goes to 5 from the right of f of x. This is going to go to infinity. You know what's going to come next. So next question is, as x approaches to 5 from the left-hand side, where is our function going? So let's take a look. So here's x equals to 5, right? So our x is going to travel towards 5 from the left-hand side. So what we're looking at is this tail end of the graph. So therefore, as x approaches to 5 from the left-hand side, the graph is going to shoot down towards negative infinity. Let me write that out. And then let me just use a different color so that I can color code it. So this portion here, where can I write this? As x approaches to 5 from the left, what we're looking at is this tail end of the graph. And again, in calculus notation, we write this as limit as x approaches to 5 from the left of function f of x equals negative infinity. Next question is, find the domain of f of x. So remember, the domain values are all the x values, right? So basically what you need to do is you need to pluck out all the x values where the graph is defined. So these are my x's, and then your graph is defined from negative infinity all the way up to 5. But it's never going to touch this vertical asymptote here. All right, so that means that our domain is going to go from negative infinity to 5, but we have to put an open parentheses here. And then on the right-hand side of the vertical asymptote, notice that this tail end is never going to touch this vertical line. So here we're going to start from 5 open all the way towards positive infinity. So in an interval notation, we write this as negative infinity to 5 open, and then union 5 to infinity. Now let's just do f and g together here. So the graph is increasing on where to where. So these values must be the x values. And also when you look at the graph, you have to look at it from left to right. That's how you analyze it. So here, right, if I travel from left towards the right-hand side, this graph, is it increasing? Is it going? No, it's actually decreasing now, isn't it? Right? And then let's take a look at the other side of the vertical asymptote. So if I look at the graph from left to right, then is it increasing? Remember, you got to look at it from left to right. So in this case, no, this guy is decreasing from here. So the answer to this is the graph is increasing on nowhere. So I'm just going to put none. Okay, now let's talk about the decreasing portion here. Okay, so let me just go like this again. So if I look at the graph from left to right, then do you see that this whole thing, this curve on the left-hand side of the vertical asymptote is certainly decreasing. So where is it decreasing from? Those are x values, so you're going to have to go from negative infinity all the way up to 5, but 5 is not included. Now, let's take a look at this graph over here now. So, what is it doing? So if I look at the graph from left to right, then this is definitely decreasing. So where is it decreasing from? 5 all the way up to infinity, but 5 is not included. So therefore, the graph is decreasing on negative infinity to 5, and then 5 to positive infinity. I'm running out of room, but then what else is new, right? Now let's try to compute the range of f. So again, range of f is the y value. Now when you find the range, you have to look at the graph from bottom upward. So here, where is the y value starting from? Isn't it negative infinity? And then if I look upward, and then how far is the graph going to go? Y equals to 0, right? Because this tail end is never going to touch this x-axis, which is the same thing as y equals to 0. So for this piece of a graph here, our range is going to be from negative infinity to 0. Now let's analyze the other graph, which is this one. Again, we have to look at the graph from bottom upward and then collect the y values. So it looks like this is going to start from y equals to 0, but it's never going to touch the x-axis. So it has to be starting from open 0. And then if I keep looking upward, then this tail end is going to shoot up to infinity, right? So in this case, the range of f is going to be negative infinity to 0, union, and then 0 to positive infinity. Let's take a look at this example. It says, given the graph, find the following. So here's the graph of g of x, which is negative 1 over x minus 2. You know what? Please pause the video and try this on your own to see what you get. So the question that's being asked are from A through J. Try it. And then it is okay if you make some mistakes. That's how we learn, right? So go for it. Hopefully, you're able to fill in all the blanks here from A through J. So let's take one thing at a time. So let's go with part A. It says, as x approaches to infinity, where is our g of x going? So let's take a look. So as x is going to infinity, remember, g of x values are the y values, right? So where is this tail end approaching to? Y equals to 3, isn't it? So here, as x goes to positive infinity, g of x is going to 3. I'm purposely using different colors here so that you understand which tail end of the graph that we're analyzing. So here, what we just did was we analyzed this tail end here. Let's do part B. As x approaches to negative infinity, g of x approaches to what? Okay, so again, as x travels towards negative infinity, where is the tail end of this graph going? I believe that it is going towards y equals to 3 again. So here, as x approaches to negative infinity, our graph is going to go towards y equals to 3. So here our answer is going to be 3, and the tail end that we were just analyzing is this tail end here. Part C, as x approaches to 2 from the right, g of x goes to where? So here is the vertical asymptote, x equals to 2. Now x is approaching to 2 from the right-hand side. So those of you who kind of get confused because you have two different pictures in one graph, just take one graph at a time. So if I approach the 2 from the right, which graph are we looking at? This graph here, or is it this graph? It's going to be the graph in quadrant 4. So just forget about this side for now. Let's just focus on the graph that's defined on quadrant 4. So here, as x approaches to 2 from the right, where is the tail end of the graph going? Negative infinity. So here, as x approaches to 2 from the right, g of x is going to go towards negative infinity, and the tail end that we just analyzed was this piece right here. How you doing? Are you all with me on this? I hope you are. But let's just look at part D. So here we have, as x approaches to 2 from the left, where is g of x going? So again, our x is approaching to 2 from the left-hand side. So which graph are we looking at? This graph here or this graph here? I would say the graph in quadrant 2. So here, as x approaches to 2 from the left-hand side, where is the corresponding g of x going? Positive infinity, isn't it? So here, our answer is going to be positive infinity. So what we just did was we analyzed this tail end of the graph. Now let's find the domain of g. So the domain of g is all the x values where the function g is defined. Okay, so let's take a look. So first of all, we got two pieces of graphs going, right? So here, I believe that this graph is defined from negative infinity all the way up to, we're not looking at the y value, we're looking at the x value, isn't it too? Because this graph is defined from negative infinity all the way down to 2, but it's never going to touch 2. So how do we express that in interval notation? Is going to be negative infinity to 2, open. And we still have the other graph to look at. So let's take a look at this one, right? So remember, when we look at the graph, especially when we're finding the x value, so you got to look at it from left to right. Okay, so let's take a look at this piece of graph. Let's look at it from left to right. So where is the graph starting from? X equals to where? 2, but this tail end is never going to touch 2. So here we should have an open parentheses with the 2 in it. And then this graph is defined all the way up to infinity. So in this case, our domain of g is going to be negative infinity to 2 union open to positive infinity. Now let's go with the range of g. So again, range values are set of all y values. So we're going to be collecting all the values of y where the graph is defined. So when we look at the graph to determine the range, you have to look at the graph bottom upward. Okay, so let's take one thing at a time. So let's take a look at this graph right here. Again, we're looking for the y value. So where does the y value, quote unquote, begin? Isn't that start from negative infinity, right? And then it's going to go all the way up to, what the heck is this? Y equals 3? So when we're analyzing just this piece of a graph, the range is going to go from negative infinity to 3, but this graph is never going to touch the y equals to 3 axis. So here, we're going to start with the range of g is going to be from negative infinity to 3, and then open. Now we should be able to look at the graph that's defined in quadrant 2. Again, we're looking at the y values, right? So where does the y value begin? Well, y value begins around y equals to 3, but it's never going to touch 3, but that is okay. So we're going to start from open 3, and then where is the graph defined here? All the way up to infinity. So here, the range is going to be negative infinity to 3, and then union open 3 to positive infinity. Now let's do part G. The question is, g of x is increasing on which interval? So here, we're looking for the interval consisting of all the x values. And again, when you look at the graph, you have to look at it from left to right. Okay, so keep that in mind. So is our g of x, so if I look at the graph from negative infinity to all the way up here, do you see that the graph is rising? Right, so in this case, graph is increasing from negative infinity all the way up to, what was this again? X equals to 2. How quickly I forget. I swear, getting old sucks. So for this piece of a graph, which lies in quadrant 2, we have a rising graph. So here, g of x is increasing on, let me just try to write this, negative infinity to x equals to 2, but it's never going to touch 2, so I better have an open parentheses around it. And now let's analyze the graph that's defined in quadrant 4. So again, I need to look at this graph from left to right. So if I look at this graph from left to right, I believe that it is increasing. Remember that increasing values are all the x values that we're looking at. So where does it start? X equals to 2, but it's never going to touch 2. So we're going to have an open 2. And then this graph keeps growing and growing and growing. So in terms of an x value, it's going to keep increasing up to positive infinity. So here our answer is going to be g of x is increasing on negative infinity to 2, union open 2 to positive infinity. I think now we can answer h, because look at it. G of x, both graphs are increasing, right? So there is no way that g of x is decreasing. So here I will just put nowhere. All right, 2 more things we got to do. Vertical asymptote. So that one's easy peasy, Where's the vertical asymptote? Is x equals to 2. Remember that x equals to 2 is an equation, not a point. X equals to 2, by the way. There is a big difference. So we have a vertical asymptote at x equals to 2. And lastly, horizontal asymptote. So where is the horizontal asymptote? Is right here. Now, what is the equation of that line? Is y equals to 3. So here, horizontal asymptote is y equals to 3. Our next topic is to analyze the vertical asymptotes. Now, in picture-wise, we know what the vertical asymptotes are going to look like. But here, it says the line x equals to c is a vertical asymptote of the graph of a function f if f of x approaches to infinity or negative infinity. So let's take a look at this graphically here. So pretend that x equals to c, this dotted line, they're vertical asymptotes. Okay, so there are 4 cases that our function f of x can approaches to that x equals to c. So for the first 2 pictures, right? Do you see that? Pretend that this is like a tail end of the graph. So here, right, if we could approach c from the right hand side. And where's the tail end going? Towards negative infinity. And let's take a look at this graph. So here, x is approaching to c from the right hand side again, but where's the tail end going? Positive infinity. Now the last 2 cases are, our graph is approaching to c from the left hand side. So let's take a look at this one. So as x approaches to c from the left, our tail end of the graph in this case goes to negative infinity. And for the last case, as x approaches to c from the right hand side, this tail end is going to go towards positive infinity. So this statement is legit because look, it says the line x equals to c is a vertical asymptote if f of x approaches to infinity or negative infinity. So all 4 cases here, do you see that our f of x is either approaching to infinity, negative infinity, and positive infinity? Anyways, let's look at the next one. It says identifying vertical asymptotes of a rational function. It says consider a rational function f defined by p of x over q of x, where p of x and q of x have no common factors other than 1. This is the key word, no common factors. If c is a 0 of q of x, then x equals to c is a vertical asymptote of the graph of f. So the statement is basically telling you is this. So suppose, right, we got f of x equals maybe x plus 1 and then x minus 2, whole thing divided by x minus 2, and then let's just go with x plus 3. So here, do we see that we have a common factor of x minus 2, right? So we can easily cancel these 2. So in order for us to determine the vertical asymptote, you need to cancel the common factors. And then you set the denominator goes to 0, and then you solve for x. So after I simplify it, we get x plus 1 over x plus 3. So then you just set the bottom equals to 0, solve for x, so x equals to negative 3 is going to become the vertical asymptote. Now, I used to get so confused between finding the vertical asymptotes in the domain of a function when I was taking the same exact class. So to find the vertical asymptote, you cancel out the common factors. In order for us to find the domain of a function, right, you do not cancel anything. You just take the denominator as is. So here's the same function. In this case, right, if we have to find the domain, let me just write everything. Domain of f, the restriction's going to be what? X cannot be 2, and then x cannot be -3. So again, do not cancel out the common factors to find the domain of f. Because look, this expression here is what? After we canceled out by x minus 2, right? So if you're asked to find the domain of this, x plus 1 over x plus 3, what is the domain? What's the restriction? X cannot be -3. And that is the only restriction that we get if we cancel out the common factors. However, in the domain, you do not. Just keep it the way it is. Let's take a look at example 4. Find the vertical asymptotes. So part A, we're given r of x equals x plus 2 over 3x squared plus 8x minus 3. The first thing we need to do is to factor the denominator. So let's work it as a side work. I don't know which method that you like. So those of you who like to use the AC method, I can do that. So here's AC and a B. So A times C is -9. And then B is +8. So first of all, we need to determine the signs, right? So when I multiply these two out, it has to be -9. So which means that one has to be positive, one has to be negative. So do that portion first. And then next, get all the factors of 9. So which is 1 and 9, 1 times 9, 3 times 3, and then 9 times 1 again. So here, oh, I see it already. So here, right, if we put 9, +9, and then -1, that is going to add up to +8. So here, if you're going to use this method, we're going to have +9 and then -1. So now, again, these two side numbers that we just came up with, this, I can't even point right now. Where is it? Okay, here we go. These two numbers are decomposition on the middle term. Okay, so then here, let me see. So therefore, this 3x squared plus 8x minus 3 is going to be 3x squared plus 9x minus 1x and then minus 3. So next step, you got to group up the first two and then group up the last two, factor by grouping. So what's the greatest common factor from the first group is 3x. Then we're going to have x plus 3. And then minus, now be careful right here. So what's the common factor of 1x and then 3? There's nothing, right? So here we're just going to leave it as is, but watch out for the sign. So first one has to be x. Right? And the next one has to be +3. Do you see that? Because after I distribute the negative signs in there, do you see that we get exactly the same expression, -1x minus 3? But anyway, so here, there's an invisible one sitting here, by the way. So here, we'll get x plus 3, and then 3x minus 1. So that is the factored form for the denominator. So let's write that out. So this becomes x plus 2, and then whole thing divided by x plus 3, and then 3x minus 1. Okay, so now let's take a look at this. Do we have any common factors? Nope. So in this case, what we need to do is set the bottom equals to 0, and then you just basically solve for x, and those are going to be the vertical asymptote. Okay, so let me just write everything out. So now we have to find the zeros. Okay, so in this case, x plus 3 equals to 0, which means that we got x equals to -3 is one of the vertical asymptote. And then we have 3x minus 1 equals to 0, which means that our x is going to be 1/3. So therefore, we have a vertical asymptote at x equals to -3 and x equals to 1/3. So here is the graph of r of x. My apologies, I just drew this by hand. So if you graph this on your graphing calculator, you better see the same exact graph. And again, graph will never, ever, ever cross the vertical asymptote. Let's look at part B. We're given y equals x squared minus 2x minus 24 for the numerator, and the denominator is x squared plus 10x plus 24. So again, what we need to do is, yes, we must factor. Don't hate. You must become one with factoring. We got this. So let's take one thing at a time. So let's do a side work for the numerator first. Okay, so side work. So we got x squared minus 2x minus 24. You can factor however you like, all right? But most of you probably like the AC method, so let me try to do it that way. Where in the heck can I write this? I'll just write it right here. Okay, so AC and a B. So the A is 1, right? And then C is negative 24. So here you're going to have a negative 24. On the bottom, B is going to be negative 2. So again, if I multiply the two side numbers, it has to be negative. So that means one has to be positive, one has to be negative. So let me just first determine the sign. And then you just write down all the factors of 24 that you can think of. So 1 times 24, and then 2 times, what is that? 12, 3 times 8, and then 4 times 6. And then the role reverses, right? And it's going to go 6 times 4, 8 times 3, and so forth. So do you see any combinations here? So whatever it is, it has to add up to negative 2. So I would choose 4 times 6. Does that sound good to you? So here, right, I would put negative 6 and then positive 4. So that way when we add, you'll get negative 2. So let me just do that real quick. So then here you're going to have, what the heck did I just say? Negative 6 and a positive 4, right? Okay, so then what's going to happen is that that polynomial becomes x squared plus 4x, and then minus 6x, and then minus 24. So then, again, group up the first two, group up the last two. So then here, greatest common factor is x. So we get x, factor out the x, and you're going to have x plus 4 minus 6 is the greatest common factor. And then here you're going to have x next step. Be careful the signs, right? Because you have a negative on the front. So this is going to be positive 4. So then factor out the x plus 4. And the remaining is going to be x minus 6. So that will be the numerator in factored form. Now let's take a look at the denominator. Okay, so the denominator is x squared plus 10x plus 24. All right, so then AC is going to be 24. And then our B is going to be 10. So the signs are going to be either negative, negative, or positive, positive, because negative times the negative will give us positive, and then positive times positive will give us positive. Now, but the thing is, when we add them together, right, it has to add up to positive 10. So if I have a negative, negative, is that going to add up, not multiplying, add up to positive value? No. So that means that our sign has to be both positive. Okay, so now I think we're ready to do this. So we already got the factors for 24 by doing the denominator, and just kidding, numerator. So what combination looks good? I think 4 and 6 is going to work out again. So let me just write 4 and a 6. So when I multiply that, it's going to multiply to 24. And if I add them, it's going to add up to 10. So here, let me try to rewrite this. You got a x squared plus 4x plus 6x, and then plus 24. Okay, group up the first two, group up the last two. So the greatest common factor is x. I'm going to factor that out. Rewrite this as x plus 4 in a quantity, and then plus greatest common factor of 6x and 24 is 6. And then here you're going to get x plus 4. So then this becomes x plus 4, and then x plus 6. So this is going to be the factored form of the denominator. So here it is. Now, remember what we're doing. We're trying to look for the vertical asymptote. So vertical asymptote is cancel what you can, then set the denominator goes to 0. So here, let me just write every step out here. So let me just go the vertical asymptote, cancel the common factor. Okay, so if we do that, then we get to kill x plus 4. So then what remains here is x minus 6 over x plus 6. And then you analyze the denominator. You set the bottom equals to 0. And then you just solve for x. So which means that we're going to have x equals negative 6 is going to be the vertical asymptote. Now, if you're asked to find the domain of y, right, then again, you do not cancel this. So the domain restrictions are going to be x cannot be negative 4, and then x cannot be negative 6. Now, every time you were able to cancel out the common factors, right, the 0 of the common factor becomes this thing called a removable discontinuity. We talked about that a little bit earlier, but let me try to graph this out. So here is the graph of our function that we're talking about. Now, the figure, or I should say the shape of the graph, is precisely x minus 6 over x plus 6, by the way. So if you graph x minus 6, x plus 6, then you should get this graph. However, we cancel out the x plus 4, right? Which means that the 0 of x plus 4, which is x equals to negative 4, becomes a removable discontinuity, which means that your function is not going to be defined at x equals to negative 4. So as you see, oh my gosh, can you see this? I'm so sorry. So do you see this point right here? It says negative 4 comma undefined. So there is a little open dot right there. So this is called the removable discontinuity, because if I remove it, it will be continuous. And here's that vertical asymptote, x equals negative 6. Let's do just one more. So here's h of x equals 6x over x to the 4th plus 1. So here, you cannot factor x to the 4th plus 1, but if you don't see that right away, try to find the 0 of the denominator, right? So let me just write it out, 0 of x to the 4th plus 1, right? So you're going to set this equaling to 0, then you're going to have x to the 4th equals to negative 1. Could that ever happen if x is a real number? No, because the solution for this is going to be imaginary, which means that the denominator has no real zeros, therefore h of x has no vertical asymptote. All right, our next topic is the horizontal asymptote. So let's read the definition. It says that the line y equals to L is a horizontal asymptote of the graph of a function f if f of x approaches L as x approaches infinity or negative infinity. Using the calculus notation, we write limit as x goes to infinity of f of x equals to L, or limit as x goes to negative infinity of f of x equals to L. Just like when we did with the vertical asymptotes, remember there were 4 cases. So it's horizontal asymptotes. So let me just draw a 4 different graphs, and we'll just analyze the definition. So of course, this black line is x-axis, and then the vertical one is y-axis. And this pink dotted one is going to be our horizontal asymptote defined by y equals the some y value of L. So here are the 4 cases. Let's look at the first case, which is the first graph. So here you can do limit as x approaches to negative infinity. Where is this tail end going? It's going towards y equals to L. So here is the expression in calculus notation. So if you don't like it, this is exactly the same thing as x goes to negative infinity, our f of x is going to approach to L. Now let's take a look at the second graph, right? So again, this you can think of it as limit as x approaches to negative infinity of this function here. Where's this tail end going? Towards L. Now the next graph is the limit as x approaches to positive infinity. Then this graph is also going towards L, isn't it? And the last picture, limit as x goes to infinity, this tail end of the graph is approaching to L. Therefore, the definition does make sense because it says line y equals to L is a horizontal asymptote if f of x approaches L as x approaches to infinity or negative infinity. Isn't that what we just talked about? They're all x is going either negative infinity or positive infinity. And what is our answer? All the values are L. Okay, next what we're going to do is we're going to learn how to find the horizontal asymptotes of a rational function. So it says let f be a rational function defined by f of x equals a sub n x to the n blah 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 to a sub 0, and then the denominator is notations b sub m x to the m all the way down to the constant term b sub 0. So basically the idea is this. Do you see that the degree on the top is going to be of degree n because highest degree is given by n. So here the top is degree is n. Now on the bottom, what determines the degree is m. I don't know, can you see that okay? I'm so sorry. So here the point is this. The point is that the denominator has degree of m. Okay, so keep that in mind and let's read this. It says the definition of f of x indicates that n equals the degree of the numerator and m equals the degree of the denominator. That's exactly what I just mentioned. All right, so we got three cases going on. So it says the first one is if n is bigger than m. So the degree on the top is bigger than degree on the bottom. Then f has no horizontal asymptote. Now, if n is less than m, which means degree of the top is less than the degree of the bottom, then the line y equals to 0, which is same thing as the x-axis, becomes the horizontal asymptote. And case 3 is this. What if the degrees are the same? So if the degree of the top is n, and suppose degree of the bottom is also n, right? So in this case, what you need to do is you just basically pluck out the leading coefficient. So that's exactly this is telling you. So the line an over bm is the horizontal asymptote of f. So because look, what's the leading coefficient on the top? A sub n, right? What's the leading coefficient on the bottom? B sub n. Now this happens when the degrees are the same. Let's do some examples. Example 5, find the horizontal asymptotes. So the first one, we're given f of x equals 5x squared minus 3x all over 4x squared plus 1. So first, what you need to do is you have to determine the degree. All right, so then here, do you see that the degree on the top is 2? So degree on the top is same thing as the degree of the bottom. The BOT means bottom. So in this case, what's going to happen is that y equals the leading coefficient is going to be the horizontal asymptote. So here, therefore, y equals 5 over 4 is the horizontal asymptote. Part B, we're given g of x equals 5x cubed plus 2 all over 3x minus 10. So here, what do we got going on here? So degree on the top is 3, which is greater than degree 1, which is on the bottom. So in this case, it would be case 1. So this g of x does not have any horizontal asymptote. Let's do part C. H of x equals 6 over 4x squared plus 1. So in this case, our degree on the top is degree 0. Constant's degree is 0, by the way. So degree of the top is going to be less than the degree of the bottom. So which case is this going to be? That will be case 2. So in this case, y equals to 0 is going to be your horizontal asymptote. Now, given the rational function, the graph will never, ever, ever touch nor crosses the vertical asymptote. However, for the horizontal asymptote, sometimes graph can touch or crosses the horizontal asymptote. So how do we know? How do we know that the graph is going to cross the horizontal asymptote is our next topic actually. So here we go. How to find where a graph crosses a horizontal asymptote. It says a graph of a rational function will not cross a vertical asymptote. However, the graph may cross a horizontal asymptote. Let y equals to L be a horizontal asymptote. Dear Lord, how many asymptotes do I need to say in one paragraph? Anyways, to determine where a graph crosses a horizontal asymptote, find the solution to the equation f of x equals L. Those values of x are where the graph of f crosses the horizontal asymptote. Man, I don't know about you, but I'm pretty sure that I'm going to have a nightmare about asymptotes. But anyways, let's do some examples. Example 6, find the horizontal asymptote and determine, if any, where the graph crosses the horizontal asymptote. So let's first look at this example. We're given g of x equals 3x squared plus 8x minus 5 all over x squared plus 3. So first of all, do we have a horizontal asymptote to begin with? I would say yes, because look, the degree on the top is same thing as the degree on the bottom, isn't it? So in that case, your horizontal asymptote is going to be the y equals the leading coefficient on the top and the bottom. So here, I know my handwriting is getting so bad, I'm so sorry. So I wrote degree of the top is same thing as the degree on the bottom, which implies that horizontal asymptote is y equals, that's his leading coefficient over leading coefficient. So in this case, our horizontal asymptote is going to be at y equals, so the leading coefficient on the top is 3, leading coefficient on the bottom is 1. So y equals to 3 is the horizontal asymptote. So now let's determine whether this rational function is going to cross y equals 3. In order to do so, what we need to do is we need to set g of x equals the horizontal asymptote, which is going to be 3. Now, our g of x is given by 3x squared plus 8x minus 5. And then whole thing divided by x squared plus 3. Now, we're going to set that equal to 3. Now, 3 is same thing as 3 over 1, isn't it? Okay, so to simplify this, if you know the cross multiplication rules, go for it. But more formally, you can multiply both sides by the least common denominator. So the least common denominator of x squared plus 3, and then 1 is x squared plus 3. So multiply both sides by, I'm running out of room, x squared plus 3. And then multiply here by x squared plus 3. Okay, so then if we do that, do you see that this x squared plus 3 and then this one is going to cancel each other out? So what's going to happen is we're just left with 3x squared plus 8x minus 5 equals 3 times x squared plus 3. Now remember what we're doing. We have to solve for x. Okay, so then what I would do is, let me just rewrite the left-hand side of it. Let's distribute the 3 to each term. Then you're going to have 3x squared and then plus 9. Now, let's just try to bring everybody on one side. And what can I do here? So first of all, I can subtract 3x squared on both sides, right? Okay, so if we do that, what the heck do we get? So 3x squared is going to cancel out. So we have 8x minus 5 equals to 9. Okay, so now I think we can solve for x. So add 5 to both sides. Oh gosh, that is supposed to be a straight line. Oh well. So then what do we get? We have 8x equals 14. Now dividing by 8, we're going to get x equals 14 over 8, which is going to reduce down to 7 over 4. Therefore, our g of x is going to cross, so crosses the horizontal asymptote at when x is 7 over 4, and then what is the y value? Y equals 3. Because look, y equals g of x, right? So we have y equals g of x, so 3 is going to be the value of y. So let me just box that. So here's the graph that we were just talking about. And so this blue one is our g of x, and this is our horizontal asymptote, y equals to 3. Notice that they intersect here at 7 over 4, which is 1.75, comma, y value is 3. So yes, a graph can cross the horizontal asymptote. Let's take a look at this example. So we're given h of x equals 8 over x squared plus 4x plus 4. So step number 1, let's determine if we have a, not the vertical, sorry, the horizontal asymptote or not. So here, let me see, the degree. What's the degree on the top? Constant's degree is 0. So the degree on the top, in this case, is smaller than the degree on the bottom. So in this case, do you remember? Y equals to 0 is going to be the horizontal asymptote, which is the x-axis. And just for fun, we could factor out the denominator, but in order for us to determine the horizontal asymptote, you don't have to factor, but I'm going to just because. So this is going to factor into x plus 2 and then another x plus 2. So with that said, can you all tell me, do we have a vertical asymptote or not? I say yes because the 0 of the denominator becomes the vertical asymptote. But anyway, so that's not what the question's asking. So let's try to figure out whether this graph is going to cut across the horizontal asymptote. So how do we do that is you basically set your h of x equals the horizontal asymptote. So that's going to be 0. So if we do that, we're going to have 8 over x squared plus 4x plus 4 equals to 0. Now, again, you can just multiply this by the least common denominator. So in this case, it's the trinomial of degree 2 there. So let me just go, oh man, I'm going to run out of room again. So you got x squared plus 4x plus 4. Okay, and then here I need to multiply here by x squared plus 4x and then plus 4. Okay, so let's see what kind of funky thing is about to happen. So here we can cancel out this trinomial. So on the left hand side, what we have left is going to be 8 equals. Now here, 0 times anything is 0, isn't it? So here, what do we get? 8 equals to 0. Is that true? I don't think so. So this is a contradiction, or this cannot happen, which means that h of x does not cross the horizontal asymptote. Here's the graph of h of x. So notice that we talked about this earlier, although that's not what the question was asking. But remember, x equals to -2 becomes the vertical asymptote, which makes sense. Here it is. And then let's look at the graph. This graph, I know it's kind of hard to see on the tail end, but this is never going to touch the x-axis, which is y equals to 0. In this case, this becomes the horizontal asymptote. Just when you thought we're done talking about the asymptote, I'm so sorry, but there is another kind of asymptote, which is called a slant or oblique asymptote. So let's just read through what it says. It says, identifying a slant asymptote of a rational function. It says, a rational function will have a slant asymptote if the degree of the numerator is exactly 1 degree greater than the degree of the denominator. So this is a very important condition. So the degree on the top has to be exactly 1 degree bigger than the bottom. For an example, f of x equals 3x squared plus 1 divided by x minus 2. Notice that the top is 1 degree, exactly 1 degree higher than the degree of the bottom. So in this case, yes, we're going to have a slant asymptote. So is it okay if I put slant asymptote SA? Whereas if we flipped it, suppose g of x is x minus 2 over 3x squared plus 1, notice that the top degree is 1, bottom degree is 2, so there should not be any slant asymptote. So in this case, no slant asymptote. Another example would be h of x equals, I just made this up, 3x to the fourth plus 1 over x minus 2. Yeah, the top degree is higher. However, in order to have a slant asymptote, it has to be exactly 1 degree higher than the degree of the bottom. Sorry, top degree must be exactly 1 bigger than the degree of the bottom. So in this case, again, there should not be any slant asymptote. So no slant asymptote. And now the question is, how do you find the slant asymptote? So it says, to find an equation of a slant asymptote, divide the numerator of the function by the denominator. The quotient will be linear and the slant asymptote will be of the form y equals the quotient. So you're going to be dividing the top divided by the bottom, and only part that you care about is the quotient. Even if you get a remainder, just forget about the remainder. So here's the summary sheet that I made up. So let's just go over this. So because we learned what vertical asymptotes, horizontal asymptote. Now, for the love of God, we got the slant asymptotes going on. So let's take a look. Given the rational function p of x over q of x, you can find the vertical asymptotes, factor p of x and q of x, then cancel the common factors. Then set the denominator equals to 0 and solve for x. And then horizontal and slant asymptotes. Oh, by the way, if you have a horizontal asymptote, right, there is no way that you're going to have a slant asymptote, and vice versa. So it's either going to be horizontal or slant. But anyways, let's take a look at case 1. If the degree on the top is less than degree on the bottom, then the line y equals to 0, which is the x-axis, is a horizontal asymptote. Case 2, if the degree on the top is same thing as the degree on the bottom, then the line y equals leading coefficient on the top over leading coefficient on the bottom is a horizontal asymptote. Alright, now let's look at case 3. So suppose that the degree on the top is bigger than degree on the bottom. So there are two cases here. So if the degree on the top is 1 more than the degree of q, which is degree of the bottom, then the line y equals ax plus b, which becomes the quotient if you divide the top divided by the bottom. So that becomes a slant asymptote. Now case B, if the degree of top is 2 or more higher than the degree of the bottom, then we're not going to have any horizontal nor slant asymptote. Let's do this example. Example 7, find the asymptotes of h of x equals negative 2x squared minus 3x plus 7, whole thing divided by x plus 3. So first, let's see if the numerator is going to factor or not, because if it's factorable, we should factor it. But looking at this, I don't think it is factorable, so let's first go with the vertical asymptote. So the vertical asymptote, how do you find it? Is you set the denominator equals to 0 and then you solve for x. So here, we're gonna have x plus 3 equals to 0, which implies that x equals negative 3 is going to be our vertical asymptote. Next, let's do the horizontal asymptote. So here, degree on the top is bigger than the degree on the bottom. So in this case, do you remember? No horizontal asymptote. Now, what about the slant asymptote? I think there is one because take a look. The degree of the top is exactly 1 degree higher than the bottom. So that guarantees that, yes, we will have a slant asymptote. To find it, what we need to do is we need to perform the long divisions of polynomials or synthetic division to divide the numerator by the denominator. I think the synthetic division is way easier, so let's do that. So first, what we need to do is we have to write our denominator of the form x minus c to determine the value of c. So in this case, we have x plus 3. Now we can rewrite that as x minus minus 3. So here our value of c is going to be negative 3. So let's go. We got a negative 3. What do we got? Negative 2, negative 3, and a 7. All right. Drop down the negative 2. Multiply with the negative 3. You get 6. Add 3. 3 times 3 is 9. So here we're going to have a negative 9. So the remainder is going to be negative 2. So let me just write down the answer. So what the heck does this mean? When you divide the top by the bottom, our answer is going to be negative 2x and then plus 3. And then remember, negative 2 is going to be the remainder, but how do you write it? Is negative 2 over the divisor, which is going to be x plus 3. But the remainder portion does not matter when you're trying to determine the slant asymptote. So all you have to do is we need to take this and then set that equal to y equals. So therefore, we have a slant asymptote. And the equation of that is going to be y equals negative 2x and then plus 3. So here's the graph of our h of x and the slant asymptote. So the red curve altogether is our function h of x. And then this slant asymptote right here is given, the equation's given by y equals negative 2x plus 3. Let's do another one. So we have f of x equals 9x cubed minus 5x plus 4, whole thing divided by 3x squared plus 2x plus 1. Let's do this in order, just like what we just did in part A. So let's first go with the vertical asymptote. So what we need to do is we have to determine the 0 of the denominator. So we're going to go 3x squared plus 2x plus 1. We're going to set that equal to 0. Now, I don't think this is going to factor because look, if you want to use the AC method, that's fine. AC and a B. So A times C is 3 and then B is going to be 2. And the sign better be positive, positive, because when you add those two positives, you're going to end up with a positive 2. So only possibility for 3, the factors of 3, is 1 times 3, right? So if I put a 1 and then 3 in here, is that going to add up to 4? No. So in this case, it's impossible. So this does not factor. So let me just write that out. Doesn't factor. And then if it doesn't, remember what we need to do? Quadratic formula. Okay, so let's do it. So we got x equals, let me just write down the formula again. Negative b plus or minus the square root of b squared minus 4ac. And then whole thing divided by 2a. All right, now let's plug and chug. So what's the value of b? That's 2. So you got negative 2 plus or minus 2 squared minus 4 times a is 3, and then c is 1. Whole thing divided by 2 times a. So we have a 2 times 3. Okay, so I don't know if you see the answer already, but let me just keep simplifying it. So you got a negative 2 plus or minus the square root of 4 minus 12. Whole thing divided by 6. Now look at the discriminant. We have 4 minus 12. So do you see that we're going to get a negative value inside the square root? So there is no real solution to that equation. Let me just clean this up a little bit. Let me just finish this. So here you're going to have negative 2 plus or minus negative 8, whole thing divided by 6. So this is going to be negative 2 plus or minus 2 square root of 2i, whole thing divided by 6, which is same thing as negative 2 over 6 is what? 1/3, and then plus or minus, now 2 goes into 2 ones into 6, how many? 3 times. So here you're going to have square root of 2 over 3i. So regardless of it, we have an imaginary solution here. So in this case, we can conclude that there is no vertical asymptote. Next, let's check for the horizontal asymptote. So again, the degree on the top is bigger than the degree on the bottom. So in this case, we do not have a horizontal asymptote. However, Do you see that we're going to have a slant asymptote because the top degree is 3? That's exactly 1 higher than the degree of the bottom, which is 2. So let me just answer the horizontal asymptote. None. Now let's find the slant asymptote. So in this case, again, we need to divide the numerator by the denominator. Now, unlike the previous example, remember the previous example was much simpler because the denominator was given by x plus 3, so therefore you were able to use a synthetic division. However, for this problem, we cannot. So we actually have to do a long division. So let me go into the next page. All right, let's do it. So first what I'm going to do is I'm going to set up the long division. So let me first write down the numerator. Are we missing any term there? Yeah, we don't have x squared term. So we're going to replace that with a 0x squared. But anyways, let me just write this like this, 9x cubed plus 0x squared, and then minus 5x plus 4. Now we're going to divide that whole thing by 3x squared plus 2x plus 1. Alrighty, so let's go. So first of all, what we need to do is what times 3x squared is going to give us 9x cubed. Now, if you cannot guess that, there's an easier way to do it. So let me just go like this. So determine what goes on the quotient part. You just go 9x cubed divided by 3x squared. So in this case, 3 goes into 3 once, into 9 3 times. So this is going to be 3. And then how do you simplify? X to the third over x squared is you take x and then you go 3 minus 2, the property of the exponent. So in this case, we're just going to have 3x. So that 3x is going to go up here. Does that make sense? So then let me just multiply now. So what we're going to do is we're going to multiply 3x to each term of the divisor. Okay, so ready? So we got 3x times 3x squared is 9x cubed. And then 3x times 2x is going to give us 6x squared. And then 3x times 1 is going to give us plus 3x. So then let's draw the line, and then we need to change the sign. So let me just change up the color here. So we have to change this into negative, and then also negative. Now we add vertically, so then this term is going to cancel out. That's exactly what we wanted. And then what do? This portion is going to be negative 6x squared. And then you have negative 5x minus 3x. So it's going to be negative 8x. And then drop down that plus 4. Okay, so now we continue with the procedure. So now what we need to do is you have to go what times 3x squared is going to give us negative 6x squared. So in this case, I will believe that it's going to be negative 2. Because if I distribute negative 2 times 3x squared, that's going to give us negative 6x squared. That's exactly what we want. So then here, let me just write it as negative 6x squared. Next, you go negative 2 times 2x, so it's going to have a negative 4x. And then negative 2 times 1 is negative 2. So here we go. And then we have to change the sign. So this becomes plus. This is plus. And then plus. Okay, so again, this term is going to cancel out. That's exactly what we wanted. So negative 8x plus 4x is negative 4x. And then you have 4 plus 2, so which is going to be 6. So that's going to be the remainder. However, all we care about is the quotient, which is the 3x minus 2. But don't forget to write the equation. You're going to have to write it as y equals 3x minus 2, by the way. So we're going to say that therefore we do have a slant asymptote. And what is the equation of that is y equals 3x and then minus 2. So here is the graph of y equals f of x, which is the blue curve. And then this green straight line is the slant asymptote, which we just computed, which is y equals 3x minus 2. All right, now the next one is going to be our finale for this section, which is we are going to apply everything we just learned and more in the previous sections to graph a rational function now. Yes, I know you're probably looking at all these steps going, why, right? But we can do this. So let me just go over this. So graphing a rational function, step number 1, find the x-intercepts by finding the real solutions of f of x equals to 0. Remember how to find the x-intercept? Set y equals to 0 and then you solve for x. Now, if you're given the rational function, right, p over q, if I'm gonna set this equaling to 0, all you have to do is set the top equals to 0. Anyways, let's look at step 2, find the y-intercept by computing f of 0. So this is basically when x is 0, what is the corresponding value for y? And step number 3, find the vertical asymptotes by letting the bottom, which is q of x, equals to 0. And then step 4, find the horizontal or the slant asymptote, if any. So again, you can have either the horizontal or the slant. You cannot have both of them at the same time. So here I just made ourselves a note. If degree of p is 1 more than the degree of q, then the line y equals ax plus b, which is a quotient, is the slant asymptote. Now, if the degree on the top is 2 or more, bigger than degree of, on the bottom, then there is no horizontal nor slant asymptote. And step 5, it says, if applicable, find where the function crosses the horizontal or slant asymptote. Solve f of x equals to L, where L is the horizontal or the slant asymptote. And then step 6, if a test for symmetry is easy to apply, use symmetry to plot additional points. I usually don't do this part, but you can if you want. So how do you check for the symmetry? Here's the review. F is an even function, which means that it's going to be symmetric with respect to the y-axis if f of a negative x equals to f of x. And then f is an odd function, which means the graph will be symmetric with respect to the origin if f of negative x is going to equal to negative f of x. All right, 2 more steps. Ready? Step 7, plot at least 1 point on the interval defined by the x-intercepts, vertical asymptotes, and where the function crosses a horizontal or slant asymptote. And step 8, graph that sucker. All right, let's do the last example for today's lecture here. So it says graph the function f of x equals 4x whole thing divided by x squared minus 2x minus 3. I know I just wrote graph the function. That does not mean that you punch it in the calculator and then boom, here's the picture. What we're going to do is we're going to follow how to graph the rational function that we just read together. All right, so ready? First one, step number 1, was finding the x-intercept. So since we're given the rational function, what we need to do is basically set the top equation equal to 0 and then you just solve for x. So in this case, what do we got? We got a 4x. Oh, that one's cute. There's no work here. 4x equals to 0 dividing by 4, then our x-intercept is going to be 0 over 4. Let me just write every step out, which is going to be 0. Which means that when x is 0, y is 0. That's what we just computed, right? So this is going to be the x-intercept. Step 2, let's find the y-intercept. So how do you find that? Is you set x equals to 0 and then you solve for x, which is the equivalent of saying compute f of 0. Okay, so let's do it. F of 0 is going to be 4 times 0, whole thing divided by 0 squared, minus 2 times 0, and then minus 3. So here, oh, how boring. 4 times 0 is 0. And on the bottom, we're going to have negative 3, which is going to become 0. So here, our y-intercept and x-intercept is going to be at the origin. So let me just write down 0, 0. And then this is where the y-intercept happens. So y equals to 0. Now let's move on to finding the vertical asymptote. So what we need to do is we have to set the bottom equals to 0, and then you basically solve for x. But here, look at the original function f of x. I do believe that we can factor the denominator. So let me just write the factored form. So this is going to be 4x, and then whole thing divided by, let me just put 2 parentheses here. So this is going to be x plus 1, and then x minus 3. Would that work? Let's check. So if I multiply the first term, we're going to have x squared. And then we're going to have negative 3x plus 1x, which is going to be negative 2x. And then 1 times negative 3 will give us negative 3. So we factored it correctly. So vertical asymptote, what we need to do is we need to set the bottom equals to 0 and solve for x. Okay, so in this case, what we're going to get is x plus 1, and then x minus 3 equals to 0, and applying the product to 0 principle, this is going to be either x plus 1 is 0, and x minus 3 is going to be 0, which means that x equals to negative 1, and then also x equals to 3 are going to be the vertical asymptotes. Now let's go with horizontal or the slant asymptote. So let's look at our function here. So is the top 1 degree higher than the degree on the bottom? Nope. So when that happens, you're like, thank you God, we don't have to do long division. But here, right, what's going to be our answer here? We do have a horizontal asymptote because degree on the top is smaller than the degree on the bottom. So in that case, y equals to 0 is going to be the horizontal asymptote. So there is that. And step number 5, we need to determine whether the graph is going to cross the x-axis, which is y equals to 0, and that's our horizontal asymptote. So do you remember what to do? So what we need to do is set our f of x equals to L, where L is the horizontal asymptote. So in this case, we have to set f of x equals to 0. Okay, so let's go. So our f of x equals to 0, which means that we're going to have 4x all over x squared minus 2x minus 3. And we set that equaling to 0. So again, what needs to happen is the top has to go to 0. Just like how we found the x-intercept. So in this case, let me just write every step out. Only the top has to go to 0, which means that x is 0. So the graph is going to cross the x-axis at a 0, 0, which is the origin. Now, step number 6, we have to check for symmetry, but I usually don't do this part, but let's do it just because your textbook does it. So how do you check is this? You just basically compute f of negative x, and then you just look at the output. Now, if f of negative x equals to f of x, which means that function is even, which means that the graph will be symmetric with respect to the y-axis. And suppose that this value becomes negative f of x, then that means that the function is odd, which implies that the graph will be symmetric with respect to the origin. WRT means with respect to the origin. All right, so let's check it. So check. So here's our given function f of x. So let's compute f of negative x and see what's going to happen. So f of negative x is going to be 4 times negative x, whole thing divided by negative x whole quantity squared minus 2 times negative x, and then minus 3. So which is same thing as negative 4x whole thing divided by, now negative x whole quantity squared is going to give us positive x squared. Next term is going to be plus 2x, and then minus 3. And analyze, is this same thing as f of x? No. So this does not equal to f of x, which means that function is not even. And then does that equal to negative of f of x? Nope. So in this case, it's neither, negative f of x. So the graph will not be symmetric with respect to the y-axis nor the origin. Step 7, I'm just going to call that intervals and test points. So basically what we want to do is we want to analyze the behavior of the graph, like maybe before the vertical asymptotes or in between the two vertical asymptotes and so forth. To do this, I usually draw the number line and just get an idea of how many intervals we're gonna get, where's my x-intercept, y-intercept, and so forth, and the vertical asymptotes, of course. So we had two vertical asymptotes, right? That was x equals to -1 and x equals to 3. So, but first, let me just jot down. So let's pretend that this is 0. And then -1, so we're going to have a vertical asymptote at x equals to -1, and then we're going to have another vertical asymptote at x equals to 3. And our x and y intercepts are both at the origin, right? So let me just make a fat dot right here. So this is going to be our x and the y intercept. And then we did have a horizontal asymptotes. Where was it? Y equals to 0 is the horizontal asymptote. And also we determined that the graph is going to cross the horizontal asymptote at 0, 0. So let me just write it like this. All right, now I think we're ready to make the chart. Okay, so what I did was I just copy and pasted the number line that we just drew. And here's the chart that I usually draw out. So first one, it says interval. Second one is the test point. And then third one is the value of f. And then point on the graph and location of the graph. So first, what I need to do is I need to chop this up into, in this case, what do we get? 1, 2, maybe 3, 4. Maybe we can chop this up into 4 interval, which is from -infinity to the first vertical asymptote, which is -1. So let me just write that out. -infinity to -1. And the next interval, so remember, here's the vertical asymptote, and then I know for sure the graph is going to cross here. So what I'm going to do is I want to analyze the interval from -1 to 0. And then next I want to evaluate from 0 to the second vertical asymptote, which is 3, and then 3 to +infinity. So here are the 4 intervals, so we're about to analyze. Now let's go with the next one, test point. So what the heck is a test point, right? So I want to know whether our graph is going to be below the x-axis or above. Okay, so then what you need to do is you have to pick any number that you want from -infinity to -1 and then plug that into our function f to get the corresponding y value. So let's pick, you can pick whatever you want, but test point, I'm just going to pick x equals to -2 because -2 will certainly lie in this interval. Now, what is the value of f? Which means that what is the value of f of -2? So let's compute that as a side work. So let me just go side work. So first what I want to compute is f of -2. In case we forgot, there is a function f of x. So let's compute f of -2. So let me just go like this. So that's going to be 4 times -2, whole thing divided by -2 squared, and then minus 2 times -2, and then minus 3. So then, let me see, we're going to have a -8, whole thing divided by 4, and then another plus 4, and then minus 3. So which is going to give us -8 over, so 4 plus 4 is 8, 8 minus 3 is 5. So here it is, -8 over 5 is going to be the value of y value when x is -2. So I'm just going to write that out here, -8 over 5, which is -1.6. Now, next one is the point on the graph. So the point on the graph, what we're going to get is when x is -2, our y value is going to be -8 over 5 or just -1.6. Okay, now let's check the location of our function then. So since the point on the graph is x equals to negative, y equals to negative, do you see that we're going to be below the x-axis, which is our horizontal asymptote. So here I'm just going to write it as below the horizontal asymptote. And then you keep doing the same thing for the rest of 3 intervals. So let's do this together. So let's go with the second interval from -1 to 0. So we're analyzing from vertical asymptote to the x and a y intercept. So what's between -1 and 0? There are infinitely many numbers, but let's pick the nice one. How about -1/2? So here I'm going to go x equals to -1/2. That's certainly between -1 and 0. Now what we need to do is we need to compute the value of f. So here let's just take it as another side work. We need to compute f of -1/2. Okay, so our f of x is written in pink, so then let's just plug and chug. So we got a 4 times -1/2, and then whole thing divided by -1/2 squared minus 2 times -1/2, and then minus 3. All right, so then what do we get? Let's just simplify this. So this is going to be -4/2, so which is going to be -2. Whole thing divided by -1/2 whole quantity squared is 1/4. And then next one's going to be negative, so sign's going to be positive. 2/2 is 1. And then drop down the -3. So don't freak out just because you have fraction within a fraction, because we're awesome. Okay, so then easiest way to do is this. Multiply the top and the bottom by the least common denominator, in this case 4. So here what I'm doing is this. I'm going to multiply here by 4, and then I'm going to multiply this whole thing by 4. Okay, now let's see what's going to happen. So next term is going to be, let me just write this out on this side, -2 times -4. So that's going to be -8. And then whole thing divided by, now what we're doing is we're going to distribute the 4 into each term in the parentheses here. So then, can we do this in our head a little bit? 4 times 1/4 is 1. And then plus 4 times 1 is 4. And then minus 3 times 4 is 12. Yay! No more complex fraction here. So then, let's just simplify. So that's going to equal to -8 whole thing over 1 plus 4 is 5. And then 5 minus 12 is -7. So it looks like we're going to have 8/7. So let me just fill in the box. So here what we just computed was 8/7, which is approximately, what is that, 1.14-ish? Okay, so then point on the graph, our x value was -1/2, and then our y value is positive, which is 8/7. So now let's visualize this. So where is our graph is going to be? Is it below the x-axis or above the x-axis? So here, right? Visualize. X is negative. So it's either going to be in quadrant 2 or 3, right? But y value is positive. So which means that it has to lie above the x-axis. So in this case, what we're going to get is above the horizontal asymptote. Now let's go into the next interval, 0, 3. So let's just pick x equals to 1. And then let's compute f of 1. So let me just take it as another side work. Okay, f of 1 is going to be, what do we get? 4 times 1, whole thing divided by 1 squared minus 2 times 1, and then minus 3. So which gives us 4/1 minus 2 minus 3, which is going to give us 4/1 minus 2 is, what is that? -1. -1 minus 3 is -4. So it's going to be -1. So filling the box, we have -1, and the point on the graph is x equals to 1, and then the y value is -1. So visualize again, x is positive, right? But y is negative. So in that case, do you see that if we're going to be below the horizontal asymptote or the x-axis? So I'm just going to write below the horizontal asymptote, which makes sense, right? Because remember at 0, 0, the graph must cross. So here we got from -1 to 0, we have our function is going to be above the x-axis or horizontal asymptote. And then from 0 to 3, it's going to be below the horizontal asymptote. So that does make sense. Now let's go with the last interval, 3, 0. So let's go x equals to 4. So another side work. Oh no, let me try to squeeze everything in here. So we got f of 4. So this is going to be 4 times 4, whole thing divided by 4 squared. And then minus 2 times 4 is 8. And then minus 3. So here we're going to have a 16 over 16 minus 8 minus 3. So what is that? 16 over 16 minus 8 is 8. 8 minus 3, which is 16 over 5. We're almost there. So here, when x is 4, our y value is going to be 16 over 5. And which is same thing as 3.2 exactly, no? 3.2. Okay, so the point on the graph is going to be 4, 3.2, which is 16 over 5. That says 16, by the way. Okay, so now let's analyze where is our graph is going to be. Above the x-axis or below the x-axis. So x is positive, y is positive, so it's certainly above the x-axis. So I'm just gonna write above the horizontal asymptote. Now finally it's time for us to graph everything. Okay, so what I did was I just rewrote everything that we just analyzed. So here, let me just write down the x and the y axis here. So first, let's drop down the x and a y intercept. So that's right here. So this is 0, 0. And then next, let's write down the vertical asymptote. X equals to -1. So let me just pretend this is that -1. And then, sorry, let me just write -1 and then 1, 2, 3. X equals to 3. What a pain about to write all these dots. Dot, dot, dot. Okay, there, that's good enough. So let me just denote this by x equals to -1 and then x equals to 3. And our horizontal asymptote is the x-axis. So here it is, y equals to 0 is the horizontal asymptote. Next, let's plot all the points, and this should have been -1.6. Sorry about that. Okay, so now let's plot. The first point is given by -2, -1.6. So I would assume it's kind of like around here somewhere. And the next point is -1/2, 1.4. So maybe like here. Okay, and the next one is 1, -1. So 1, -1. Oh, I'm so sorry, x and a y intercept. I'm writing over you. And then next one is 4, 3.2. So 4, 3.2. Here we go. And go back to the chart that we just drew, right? So we know for sure that our graph must cross the horizontal asymptote at 0, 0. And here are the 2 points that's between the 2 vertical asymptotes. So my guess will be this. This tail end of the graph is going to be asymptotic to x equals to -1. And then graph's going to cross here and then go through this point. And then it's probably going to be asymptotic to x equals to 3. So here is my guess. It's gonna go like this. That's good enough. Now let's analyze what's gonna happen in this region here. So the graph better cross this point here. And then go back to the chart. What does the chart say? Location of the graph. From -infinity to -1, location of the graph was below the horizontal asymptote, right? So my guess will be this. Our graph is going to go asymptotic to y equals to 0 and then asymptotic to x equals to -1. And if you're wondering, well, how do you know that it's gonna go asymptotic to y equals to 0 is, remember, the only point that's gonna cross, the graph is gonna cross the x-axis is at the origin. So there is no way that this graph can move up above the x-axis. So let me just try to draw this out. I hate graphing. Okay, hold on. No, I love it. I love it. I love it. So here is, oh my God. Jesus. Okay, that's my guess. And now let's analyze what's going on up here. Okay, so the graph has to go through this, right? And there's no way that the graph is going to cross the x-axis because the only place that's going to cross is at the origin. So, and then also if you look at the chart, we know for sure that from 3 to infinity, our graph is going to be above the horizontal asymptote. So my guess will be this. This tail end is going to go asymptotic to x equals to 3. And then it's going to go asymptotic towards y equals to 0. And if you're not too sure about it, you can compute the additional points, such as like maybe we can compute f of 5. You know what? For heck of it, let's just do it. So if I compute f of 5, then we're going to have, what is that, 4 times 5. Whole thing divided by 5 squared, which is 25, and then minus 2 times 5, which is 10, and then minus 3. So which is going to give us, what is that, 20 over 12, which is going to be 5/3, which is 1.6. So for sure, the graph is also going to cross the 5, 1.6 as well. So where is that? 5, 1.6 will be here. So this blue one is the test point. So I think this is the way it's going to go. And that's our graph. So here's the actual graph of our function. So look, we did pretty darn good. All right, I am totally done with this section. I'm sure you are so burnt out by now. So great job, everyone. And if you have any questions at all, or if I made a mistake somewhere, I make mistakes like all the time. So please let me know, okay? Then I will be talking to you during the next lecture. All right, bye.